So this video here contains a very short introduction to using the Schrödinger program, which is the program that we will be using in this course here on quantum chemistry and theoretical spectroscopy for carrying out specific quantum mechanical calculations on molecules. So to begin with, if you want to know more about this program, then you can Google Schrödinger, I already did so, and choose the Schrödinger.com site, and here you can read about the capabilities of this program here. This is a quite large program that contains a lot of different submodules capable of doing different kinds of calculations. What we'll be using here is the Jaguar module on this program here, which enables quantum chemical calculations on molecules. So visit this web page here and try to browse for information about the program. Let's start here by activating the Maestro. Now, Maestro is the graphical interface that we use in order to build and to manipulate the structures that we are going to use for the quantum chemical calculations. It looks something like this here. Maybe when you activate Maestro for the first time, you will not have this list of options up here. So what I encourage you to do is that in case you don't have this list of options here, then simply to go through them and to left click on the mouse. You can see what happens here when I do it in the reverse order here. Then maybe when you start, your interface will look something like this here. And here you don't see on the right hand side and on the left hand side, you don't see the options that are available in this program here, but you get all of this in place if you do the click with the left mouse button as I do here. And this is very handsome because we are going to use a lot of these options here in the program. Now, this is the place here where we can build and manipulate the structures, and we can use some predefined structures here. If we look at the outermost right of this program here, then for example, if I click on this molecule here, this is formaldehyde, I click on using the left mouse button, and then I click again left in the black area and formaldehyde appears. Now this is one representation of the molecule here, but I can of course choose different representations, and I can choose them from the left panel here. I can, for example, double click on this one, again left double click, and then I get a structure looking something like this. Now this is my preference structure because here I can easily see the bonds and I can also easily see the atoms here. So this is what I like to do. Now if I take the mouse and I use the middle mouse button to take down here, then I can rotate the molecule, and if I take the right mouse button, then I should be able here to translate the molecule as well. If I have placed the molecule in some weird orientation like this, for example here, and I would like to center the molecule, then I go to the left and I use the center button here, and it should automatically be placed in the middle of the box. I have a lot of other options here. In the left I can change the color for the atoms. Now I have a carbon atom in gray, hydrogen atoms in white, I have oxygen atoms in red, but of course I can change this if I wanted to have it in some other colors. And here on the right hand side here, I can do structure manipulations. So for example, I can draw additions to this structure by using the pencil. I can make a single bond to a double bond, or by clicking twice on this to a triple bond, and I can reverse this by making a double bond to a single bond and so on. I can give the molecule an overall +1 charge by clicking twice a +2 charge. I can give it a negative charge here. I can do some simple structure optimization. If you now look at the structure, when I push at this button here, you can see that it changed a little bit. What we did here was what we call a force field or a molecular mechanical calculation in order just to brush up the structure of the formaldehyde molecule here. So this is a very, very simple geometry optimization based on classical principles. So I have now built here formaldehyde. Again, this is a simple molecule. If I double click on the red cross up here, then the molecule disappears. I can easily work with much more complicated molecules. Let me try to show such one here. If I go to the applications, then if I go to the protein preparation wizard, if I'm going to do calculations on protein, then let me import a PDB file. This is the PDB file for the photoactive yellow protein. This is actually just a small protein. Let me pre-process it so that the program can find out which bonds are actually present here in this protein here. And let me just fix it because we don't want to spend more time on this. This is just to show that I can of course also study much more complicated structures, looking for example like this one here. Now this is probably a bit too big for performing quantum chemical calculations, so let's just skip it again and go back to our good old friend formaldehyde like this here. Whoops, this was a wrong representation here. Now when I want to do calculations, then I go up here in the menu, and here I have different possibilities. Let's try to look at some of them. In the application panel here, I can choose between different programs where I can perform different calculations. I said we will be most interested in doing calculations in the Jaguar program, which is quantum chemical calculation, and from this I can see that I can do single point energy calculation. That is, I can just calculate the energy for formaldehyde without changing the position of the nuclei, or I can do a geometry optimization. That is, I can try to let the program predict at which molecule distances the nuclei should be placed in order for the program to provide the lowest possible energy, that is to predict the most stable structure for this molecule here. So these are two options that we'll be looking more into later, and we will also see how to enable calculation of molecular properties like dipole moments and so on. We have a lot of different options up in this part of the box up here. For example, we can do measurements of distances. Let's try to measure what is the distance between oxygen and carbon, 1.21 angstrom for example. Then we can measure a distance before and after we do a geometry optimization, and then we can see the impact of actually having done this geometry optimization. Let's try to remove these measurements again by pushing the delete measurements. Now you can read more in the manuals that I have uploaded on Blackboard about the different functionalities that are available in this program interface here, and also as you get more and more used to work with this program here, well, then it will be much easier for you to use all these different entries and possibilities here in order to manipulate your structure and so on. So let's try here to begin to do a simple quantum chemical calculation. The first thing that we need to do is to make a project entry. It is like this, that all calculations that we do will then be saved under the name that we now give this project here. So in the workspace we create a project entry. We could call it, for example, formaldehyde, and then we create. You can see here that on the left in the interface here, formaldehyde now appears, and it means that what we do now is reference to this entry all the time. Let's go to the applications. Let's choose Jaguar, and let's do a single point energy calculation. Now you can see here that the first thing that we need to tell the program here is which charge to use, which spin multiplicity to use, and which basis set to use. Now the charge is 0, the spin multiplicity is 1 because we have a closed shell molecule, and the basis set, well, here we will choose the 631G star basis set, which you read about in the paper that I provided you. Then let's set up the theoretical level of the calculations that we are going to do. Here we can choose between density functional theory, we can choose between Hartree-Fock, or we can do MP2 calculations. These are also described in the paper that I gave you. So let's keep it to density functional theory here. We do a ground state calculation. If we would like to enable excited state calculations, which we will do later on, then we will have to mark here, but for now we will do ground state calculations, and we will use the B3lib exchange correlation functional, also described in the paper that I provided you. Under the SCF tab, here we set up the accuracy level. That is, do we want a fast calculation with maybe not that accurate, or do we want to spend a little more time on the calculation and then get a higher accuracy? Here we choose an accurate level here, which I also suggest you to do for the rest of the calculations that we do in this course here. Under the properties, we can choose to calculate, in addition to the energy, different properties like vibrational frequencies, molecular orbitals, densities, electrostatic potentials, electrostatic charges, multiple moments, for example dipole moments and so on, NMR shielding constants, and so forth. And we will be looking into these different options here in some of the other classes later on. We can also choose to include a model that accounts for solvation, but for now we will just calculate the molecules in gas phase. So let's try here just to go back here to the theory tab. You give the calculation a name. We could call it, for example, formaldehyde calc1, and you run the calculation like this. Now when you have submitted your calculation, you can see a small green button appearing down here. Already now the calculation actually finished, because now it turned gray again, meaning that the calculation has already finished. If we go now to the table and we click on this up here, then we should be able to read off the results of the calculation. So let's try to do this, and to make the table a bit broader here, we can see that we have done a calculation on formaldehyde. We have been using DFT B3lib 631G star basis set, and we predicted by this a gas phase energy that was equal to minus 114.5000 atomic units. Now if we want more detail on this, then we go to the jobs list here. We choose monitor. You point here to the calculation that you want to look more careful into, and you choose details from here. And now you have access to all the files that have been produced during this calculation here. For example, we can try to look at the log file, which contains a summary of the output calculation. From this we can see here that the program found the molecule to be in the C2V point group, and you can see here a number of energies here. Now, as we talked about and as you read in the paper that I provided you here, when we do such quantum chemical calculations here, they rely on the self-consistent field procedure here, meaning that what we do is actually that we guess first how the orbital should look like for the system, and then in a number of calculations we refine the orbitals until the energy does not change anymore for the system. So this is what happens here. You can see that we have a start energy which is equal to minus 114.49 atomic units, and then in a number of refinements here we update the molecular orbitals until this energy here does not really change much. Here we have a criterion saying that when the change in this energy here is smaller than a given threshold, then we are done with the calculation. Now we can get some more details if we go back to the details button and we press the output here. We go up in the top of this output file here. Then we can slowly scroll down here. We can see that the basis set is 631G star. The net molecular charge is 0 and the multiplicity is 1, exactly as we have provided on the input. Then we have, then we have the start geometry here in Ångström, and we have the principal moments of inertia, which you have looked at also when we have talked about rotational spectroscopy, and also rotational constants, that is the B constants that we looked at when we talked again about rotational spectroscopy here. Then by scrolling down here, you can see here you get some information here. Here the calculation starts. The number of electrons is 16, which is fine for formaldehyde. In this basis set here you will have 34 orbitals. 8 of them will be occupied because you have 16 electrons and we have doubly occupied orbitals. So it means that 26 of the orbitals will be virtual or will be empty orbitals in our system. Then you get, as before, in the log file here, the energy printed as we proceed in the self-consistent field calculation. You get a summary of the different energy terms. You remember from the Hamiltonian that we had the nuclear repulsion term. This is equal in this case to 31.21 atomic units. Then we had the 1 electron term, you can read off here. The 2 electron terms you can read off here. Of those you have the Coulomb and exchange and correlation contribution equal to this. You have the electronic energy here, and then you have the total energy here, which is the sum of the electronic energy and the nuclear repulsion energy. Then, in addition, you have printed here the energy of the HOMO orbital and the energy of the LUMO orbital, as well as some of the other orbital energies. Now you can have more of those printed if you want to, but then you will have to specify it in the input. In addition, you get printed the symmetry of each of these orbitals here. So since we had 8 orbitals occupied here, we can see here that this contains electrons, this, 1, 2, 3, 4, 5, 6, sorry, I have to read it in this way here. 1, 2, 3, 4, 5, 6, 7, and 8. So this one here should be the HOMO orbital, this is so, and this one here should be the LUMO orbital, and this is also correct here. So by this you get an estimation here of the difference between the HOMO and LUMO energy by subtracting these two numbers here, which would be a rough estimation of the excitation energy or the lowest excitation energy in our system. But we will get back to this later on here. So this was a very simple single point energy calculation here. Let's try here to go back here to the calculation on formaldehyde, and then try to do also a geometry optimization. The way we do this is again by the application panel. We choose the Jaguar, we choose the optimization button now. Again we have the entry formaldehyde. We again reduce the basis set to just a single set of polarization functions. We go to the theory tab. Again we have density functional theory using the B3 exchange correlation potential. Under the SCF we choose the accurate level here. We have the optimization, meaning that now we are going to let the program move the nuclei in order to reach the lowest energy on the potential energy surface. We can calculate properties, for example vibrational frequencies, and so we will not do it now, but we will do it later on. And again we can also choose solvation and so on. So let's try to submit the calculation. We call it formaldehyde calc2. Now it will take a little bit longer time than before, because now we are going to predict how the nuclei should be placed in order for the molecule to have the lowest energy. This we did not do before. Here we just calculated the energy for the position of the nuclei that we provided. But you could see here that the calculation already finished. Let's go and look in the table. This is the new calculation here. You can see here that, well, the energy was changed slightly compared to the non-optimized case here. But actually, I mean, the changes is very, very little. So it means that we were actually able to provide a very good guess of the structure of formaldehyde here. The energy changed a little bit and it became a little bit lower. And this is exactly how it should be, because what we aim at is to place the nuclei in a way such that they get the lowest possible energy. So this is nice. Let's go back here and try to go in as before and get some more details on the file. I go now directly here to the log file. If I go to the top of this log file again, then I see that I have again something like I had before, a number of energies where I converge my self-consistent field equations in order to determine the electronic structure, the orbitals and so on, for the given set or the given position of the nuclei. And then what I do now in addition is that I calculate what is the force on each of the atoms in my molecule. This I did not do when I did the single point energy calculation. And here I can see that I have a gradient maximum and a gradient root mean square. That is where I consider all the atoms here. And ideally, this gradient here should be equal to 0 for a geometry optimized molecule. You can see this is not equal to 0. Out here we have the threshold, meaning that when these numbers here become less than the threshold that are listed out here, then the program will treat them as being 0. You can see this was the first iteration in our geometry optimization. So what the program does now is that it finds a new position of the nuclei according to the gradient information up here, and then it will repeat the energy calculation. It will calculate again the gradient, it will move the atomic nuclei again, it will again calculate the gradient, it will continue to do so until the energy change and the gradient maximum and so on are below the threshold numbers which are listed up here. And you can see this only took actually 3 steps, so I only should move the nuclei 3 times in this case in order to reach to an equilibrium position here. So by this I have now here predicted what is the equilibrium structure or the lowest energy structure of formaldehyde. Now let's try to do a little trick here by adjust what I can do clicking here on the distance. Then I can try to enlarge the distance here between the nuclei. Let me try to put it up to this. This is a quite long CO bond looking like this. Try to adjust again, delete the adjustments. Sorry, and let me go to the applications. Let me do the Jaguar, the optimization here. And let me try to run the calculation again here, now calling it formaldehyde calc 3. Let me try to see what happens now here. Probably it will take a little bit longer time because now I have given a very bad input structure with a very long CO bond length, meaning that probably the program needs to do quite many geometry optimization steps in order to go to the energy minimum here. And you can see that it actually took a bit longer than before. Let's go again here to the table. If we look at the table, this is the new calculation that I have here, and you can see here the result here of this calculation here. Let me try here to go to the monitor. Let me try to choose this one, the details. Let me try to go to the log file here. Now you remember last time that I had to do 3 geometry optimization steps. I'm already now here at the bottom of the file, and you can see that now I needed 7 optimization steps. So I needed to do more steps because I provided a bad input structure. Let me go here to the almost to the top. I don't know if you remember the gradient maximum in the previous calculation that I did. This was something 10 to the minus 3 or something. Now, because I have given such an artificially long CO bond length here, it actually become quite high. This gradient here, it was 10 to minus 1 in this case here. So if I go back here and I do the measurements again, I do the measurements here, the distance. Let me try to see what is the distance. This is 1.21, and let me try if I push the control button and then I take the No, I cannot do this. The input structure here, on the Mac I have to choose the Apple button, and otherwise I have to do the control button here, and then I get the overlay of the two structures. So the long one here is before the optimization, and the short one here is the equilibrium position, that is after I have done the geometry optimization. So this was just a very brief introduction to some of the very simple concepts that we are going to use. For now here, you should choose one of your favorite molecules, and then you should try to do a energy calculation and geometry optimization of this molecule. Go through the output files and make sure that you understand what the program does. Does it find the correct symmetry and so on? Try to look at the questions that I have written here on the lab information for you, and then during some of the next weeks we will look much more into detail about how to calculate molecular orbitals, how to visualize the molecular orbitals, how to visualize molecular electrostatic potentials, how to visualize spectra, both infrared spectra and UV spectra, and so on. So much more to come later on.